All right, in this video we're going to be looking at volumes of a revolution, and we're going to be looking at cylindrical shells. And then we'll also compare the method of cylindrical shells with the disk or the washer method, depending on which method is appropriate to use for the problem. So it states another method for finding volumes of surfaces of revolution is called the shell method. The advantage of the shell method is it can sometimes make the integration easier than using the disk or the washer method. We'll do some examples where either the disk or the washer method is easier or the shell method is easier. Instead of revolving disks or washers around an axis of revolution, we will be revolving shells or layers of an onion around an axis of revolution. So I've drawn a horizontal line for axis of revolution, okay? And we'll draw a representative shell here, okay? So there it is, and so we're going to rotate this shell about the axis of revolution. And so we'll say that the height of the shell is h, okay? Okay, and then this is think of that as like a layer of an onion, and that's going to be our width. And then P is going to be like an average radius, so it's like right in the middle of the shell. Okay, so that's the distance from the axis of revolution to the middle of the shell. So distance from the axis of revolution to the center of the shell. Okay, and then we're going to have like an inner radius, which we'll call P, and then it's going to be where so you can kind of think of you having an outer and inner radius. So when we first hit the layer of the shell or the onion there, so that's going to be P, and then minus W over 2, so it's going to be half of the width there. That'll be the inner radius. And then P plus W over 2 will be the outer radius. And we're going to go ahead and rotate this all the way around and pretend that looks nice. So we have an outer cylinder and an inner cylinder. If we subtract the outer cylinder, oops, let's not use that color because you can't see it. So you have your outer, and then you got your inner, and so you take your outer radius or your outer cylinder volume and subtract from it the inner cylinder volume, and that'll give us the volume of that shell. Okay, so for our reference, this volume of a cylinder is pi r squared h. So the volume of the shell is going to be equal to the volume of the outer cylinder minus the volume of the inner cylinder. Now the outer cylinder's volume is going to be pi, and the radius of that is the P plus W over 2 squared, and then the height minus the volume of the inner cylinder, which is pi, times the radius squared, which would be P minus W over 2 squared, and then times h. So we're going to go ahead and expand this out so we have kind of an idea of where the shell method formula comes from. Okay, so we're just going to rewrite what we had before. And we have both a pi and an h in common, so we'll go ahead and slide that out. Then we're going to go ahead and FOIL out P plus W over 2. So when we do that, we have P squared plus 2 PW over 2, so it's going to just be PW, plus w over 2 times itself is going to be w squared over 4. Okay, minus p times p is p squared. P times w over 2 and then times 2 because we're foiling, that's going to give us minus pw. And then w over 2 times w over 2, or minus w over 2 times minus w over 2 is going to be a w squared over 4. Okay. All right, so what's going to happen here is we'll still have the pi and the h, and we're going to have p squared minus p squared, so that's gone. And we're going to have pw minus negative pw, so that's going to give us 2pw. And then w squared over 4 minus w squared over 4, those are going to go. And so we have 2 pi phw. So any order in how you write that. Okay, so that's going to be 2 pi. And then p was your average radius. So that's the radius between the outer and the inner radii. Okay, h is the height. And then w was the width or the thickness of the shell, okay? And so what we're going to do is we're going to let the thickness of the shell go to 0, and so it's going to be a better and a better approximation. So that's going to give us 2 pi p of y, h of y, and then we'll call the thickness a delta y, okay? And then we're going to let delta y go to 0. And so we're going to add up all of these shell volumes, so to speak. And that gives us the integral formula, 2 pi integral from c to d, p of y, h of y, dy. And this is your shell method. Okay. So on the next screen, we're going to do a comparison. So this is from the OpenStax Calculus Volume 2, and it says comparing. Oops, we went too far here. All right, so let's go back. Oops. Okay. So it says comparing the methods for finding the volume of a solid of revolution around just the x-axis. So we're going to compare the disk, the washer, and the shell method. So you have your respective formulas there. Now, if you notice here on the shell method, you have a y there. That's your p of y. That's the distance from the representative rectangle to the axis of revolution, which is simply going to be y in most cases. And if we're rotating around a different horizontal line, it may change, or if there's some sort of gap, that may change. And then for the solid, if there's no cavity in the center, you can use the disk method. If you have a cavity in the center, you can use the washer method. And the shell method will actually work with or without a cavity in the center. Interval of the partition. So both the disk and the washer method, you're going to be perpendicular. So if you draw your radii are going to be perpendicular with the axis of revolution for the disk and the washer method. However, the shell method, you're going to be parallel with the axis of revolution. So, if you're doing disk or washer method, and you're revolving around the x-axis or a horizontal line, your integral needs to be in terms of x, and your functions are in terms of x. If you're going to do the shell method, around rotating around the x-axis or a horizontal line, then your functions need to be in terms of y, and you're going to be integrating with respect to y. Now, if you're rotating around the y-axis or a vertical line, then the disk and the washer method need to be in terms of y, and the shell method will be in terms of x. So you will never be doing a problem with the shell method is in terms of x, and then disk and washer in terms of x. They're going to be opposite, okay? All right. So let's go ahead and move on to the first example. So we'll do an example, and we're going to do both the disk washer method. I think we'll do that second, but first we'll do the shell method. Okay. And so down in the lower right-hand corner, I've drawn the p of y. That's the distance from a representative rectangle. That's going to be your shell. So that shell is going to rotate down like this. Okay. And then the h, they're calling it g of y in this case. So it's just a different variable. G of y is going to be the height of the shell there. All right. So let's move on to the next page. So what do we say? Or what are we finding? Find the volume of the solid bounded by y equals 1 minus x in quadrant 1. And then we're going to rotate and say this is rotated. Does that make sense? Find the volume of the solid bounded by y equals 1 minus x in quadrant 1, rotated. It should not say by, but about. So we're going to rotate about the x-axis, not the x-axis, the y-axis. We're going to rotate around the y-axis. And then we're going to use the shell method and the disk or washer method, whatever one applies. So first order of business, we're going to do a sketch, shade in the region here, rotating around the y-axis. And when we're doing the shell method, our represented rectangles need to be parallel with the axis of revolution or axis that we're rotating around. So we're doing the y-axis, so that's up and down. So our rectangles need to be up and down. So our functions need to be in terms of x. Okay, the distance from our representative rectangle to the axis of revolution is simply described by x. The height function is simply 1 minus x. That's the function that we're going to be rotating. So the volume formula is 2 pi, integral from a to b, p of x, h of x, dx. So it's going to be 2 pi, limits of integration, 0 to 1 on the x-axis. P of x is x, h of x is 1 minus x, dx. So it's going to be 2 pi, integral from 0 to 1, x minus x squared, dx. 2 pi x squared over 2 minus x cubed over 3. And then we're going to evaluate that from 0 to 1. So 2 pi 1 half minus 1/3. So that's going to be 2 pi times 1/6 if we get a common denominator. So pi over 3, or 1.0472 units cubed. So I was doing the shell method. We'll go ahead and look at this exact same problem, but we're going to do it with the disk or the washer method. Okay, so we'll go ahead and sketch the same region, shading the region to be rotated around the y-axis. Okay, now if we're doing the disk or the washer method, our radii need to be perpendicular with the axis of revolution, or if you're doing your representative rectangles, perpendicular with the axis of revolution. So they're going horizontal, so we need to be in a function in terms of y. Okay. So is it disk or washer? And that depends on if there's a gap or a cavity between the region and the axis that you're, or whatever you're rotating around. So you see that there is no gap there, so we're going to use the disk method. Okay. Y equals 1 minus x. That needs to be solved as a function of y. So solving that gives us x equals 1 minus y. All right, so the volume is going to be pi, integral from c to d, and then your radius squared, dy. So pi, limits of integration on the y-axis, so 0 to 1. Okay, 1 minus y squared dy. So pi, integral from 0 to 1. Go ahead and FOIL that out. 1 minus 2y plus y squared dy. So it's going to be pi, y minus y squared minus y cubed over 3 evaluated from 0 to 1. So pi, 1 minus 1 squared plus 1 cubed over 3. And so that's going to be pi over 3 units cubed, or as a decimal, you see it there. Now, it'll always be the case, if you have everything set up correctly and you integrate everything correctly, that the shell method will give you the same result as either the disk or washer method, whatever is appropriate for disk or washer. So as you're working on problems, or maybe you have problems specifically asking you to do both the shell method and disk or washer method, or they may say, hey, go ahead and do this with an integral in terms of x and then an integral in terms of y. That's kind of a hint that, one method should be disk or washer and the other should be the shell method. And so in the next 2 videos, we'll be looking at examples of taking the same region, rotating around the same line, and then kind of comparing how it looks in the shell or disk shell method and with the disk or washer method, and maybe one method is easier than the other. So we'll see you in the next video there.